Welcome to our introductory series on quantum chemistry. In this video, we're going to discuss the Schrodinger equation, that mysterious equation that you've no doubt heard about but have no idea what it means, and looking at how we're going to use that to examine atomic and molecular properties. So in this video, we're going to start with introducing the Schrodinger equation, and then we're going to talk about its meaning, and particularly these mysterious mathematical functions called wave functions, and how we can use them in chemistry to determine properties of various systems. And from that, we're going to look at the basic postulates of quantum mechanics and something called operator algebra, which is not as hideous as it may sound, and how we use that to extract useful information about these properties. So, let's start with the Schrodinger equation itself. Developed by Erwin Schrödinger in late 1925 and published in early 1926, what Schrödinger was trying to do was to develop a mathematical theory that explained the wave-like behavior of particle systems. Remember, we discussed wave-particle duality in previous videos. So he was thinking, we've got these wave-like properties, so I'm going to try to develop an equation modeled after wave equations, although certainly not the same as a classical wave equation. And he came up with a basic equation that looks like this for a single particle in one dimension. All right, so we'll notice here as we take a look at this is that we've got definitely a differential equation because we have a second derivative in our equation. But what are the various terms in this equation, and how do we use those? How do we use this equation to solve our problems? All right, so first of all, we see this H with a little cross through it, which we refer to as H bar, and that's a constant that consistently shows up in a variety of mathematical applications of quantum chemistry. H bar is just very simply H, which is Planck's constant, as you recall, divided by 2 pi. And again, because that shows up frequently in these expressions, physicists decided that rather than writing H over 2 pi every time, we're just going to call it H bar and understand that that's a fundamental constant here. This U of X term here represents the potential energy of the system, and that's an important part of what we need to do when writing the Schrodinger equation for various chemical systems, is to figure out what the potential energies and interactions are present in the system that we're studying. E represents the total energy for our system. And we see the E here after the equal sign. M, of course, is the mass of our particle. And finally, we've got this Greek character psi, and that is the Greek character psi. It looks like a little pitchfork. That is this wave function that is what we're really all about here. So what we try to do when we're solving a chemical problem in quantum mechanics is we first write a Schrodinger equation, which includes all the dimensions, and again in this case we just have one dimension, but includes all the dimensions for all of the particles and the potential energies of interaction for all the particles. And the whole point here is to just determine from solving this differential equation the wave function psi and the corresponding energy for that wave function psi. So what is this wave function psi? Well, there was some debate about that early on in the development of quantum mechanics and the application of the Schrodinger equation. We commonly today use what's called the Born interpretation, named after Max Born. So first of all, we'll note that the wave function represents the state of the system at energy E, and represents what we call a probability amplitude. And what that means is that if we take this psi star psi, where psi star represents what's called a complex conjugate, and we'll come back to that a little bit later on. And the product of psi star, the complex conjugate, and psi is what's called the probability density. Okay, so what does that mean? All right, so first of all, if psi is equal to e to the ikx, the complex conjugate just involves putting a negative sign in front of the imaginary term. And that's the general case, if you remember from complex conjugates, when you're introduced to that way back in mathematics, that when we take a complex conjugate, we're just putting a negative sign in front of the imaginary component. And it's just the imaginary component of our complex function. So, if psi happens to be real, that is, if it has no imaginary components, then psi star psi is just simply equal to psi squared. A lot of the systems we're going to be looking at will be real, so we won't have to worry about the complex conjugate. But there are a few for which the complex conjugate is indeed important. All right, so again, back to the meaning of this. So psi star psi dx, all right, where dx represents the differential dx, is the probability of finding a particle in a region of space between x and x plus dx. Now that would be an infinitesimal region of space because dx is infinitesimal. And of course, normally speaking, we're looking for probabilities associated with finite regions of space. So if we're trying to find the determine the probability of finding a particle in a finite region of space, say between 0 and 1, 0 and 1 just being arbitrary here, then we're going to integrate. Now, a clue here, as I have mentioned before, is that if we're in class and I'm asking a question about what the next step of a process might be, then more than likely the answer is integrate. We are going to be doing that an awful lot. So again, this integral from 0 to 1 of psi star psi represents probability of finding a particle in this region between 0 and 1, again 0 and 1 being arbitrary units. And again, in future videos we'll be looking at concrete, real examples where we can apply this, so perhaps it's a little bit abstract. Right now I'm sure everything seems very abstract, but we're just laying the groundwork for future use. All right, so we know that we've got this psi star psi, we got this wave function psi, and that's got what we have with regard to what we can know about probability, but also embedded in this wave function is everything that we really can know about the system in that particular state. And so the question is, how do we extract information like what's the momentum of the particle, what's its kinetic energy, things of that nature? How can we do that? Well, so we use operator algebra for that. So first of all, what do we mean by an operator? An operator is something that performs a mathematical function on a function. So for example, multiplication is a simple operator. So that's an operation, and the operator is just the multiplication sign. But derivatives are also operators because they operate on a function. We can take the derivative of a function. So the first derivative, the second derivative, etc. represent that. Another symbol that we'll see when dealing with three-dimensional systems, shorthand, is this symbol which is the inverted triangle square, which is called del squared. And this is just simply the sum of the second derivatives for the 3 dimensions in Cartesian space. So it's very simple. So rather than writing each one individually, we can write del squared and understand what that means. But again, this is an operation. You will notice that we have listed here, for example, the derivative, but we haven't indicated the function because the derivative operates on a function. So the operator itself is just the derivative, but we're going to operate on some function, f of x, when we do this. Now, we've already been introduced to one operator, and that's the Hamiltonian operator. And that was in the Schrodinger equation itself. So, for example, if we were to introduce this Hamiltonian operator represented by h here, and you'll notice actually the little caret sitting on top of that h, we use that symbol whenever referring to an operator. Okay? Because an operator doesn't stand by itself. An operator will operate on a function to give a particular result. So if we define our Hamiltonian operator as being equal to this particular set of terms here, h bar squared, negative h bar squared over 2m times the second derivative with respect to x plus the potential energy. We will note that if we go back and look at our one-dimensional single particle Schrodinger equation, that equation can be rewritten as h, the operator psi, equal to E psi. So this just corresponds to taking our operator here, okay, and operating on psi, and you can see this is what we're doing, each term independently. So the first term with the second derivative operating on psi, and then the second term is just multiplication times psi, and that's equal to E times psi. All right, now this equation is actually an example of something we call an eigenvalue equation. And very generally, eigenvalue equations are defined as equations where there's an operator operating on a function psi, and the result of that operation equals a constant times our original function psi. So that is the definition of an eigenvalue equation. And in that circumstance, we call the constant the eigenvalue, and the operator, excuse me, not the operator, but the function is the eigenfunction. Now, this is not something that happens all the time. We're going to see a number of examples where we take an operator and we operate on the function and we don't get a constant times that original function. But when we do, it's actually very, very important in quantum mechanics. So we can see that we have in the Schrodinger equation here an eigenvalue equation because we have an operator, h, operating on the function psi, giving us a constant, E, times the original function psi. All right? So E is our eigenvalue and psi is our eigenfunction. Now the importance of this is that when we get a situation where we take an operator and operate on the function, we're going to find that the eigenvalue, when we have an eigenvalue equation, the eigenvalue is what we would end up measuring in the lab. So the Hamiltonian operator is our energy operator, and when we operate on our wave function, we get E times psi. So E is what we would measure when we measure the energy in the lab. Okay, so what's the deal here? Well, it turns out that for everything we can observe in the lab, every physical observable, there is an operator that corresponds to that physical observable. For example, position. We want to measure the position of the particle. The operator for position is very simply, if we're talking about one dimension x, it's just multiplication by x. If we're interested in momentum in the x direction, the operator for momentum is this very bizarre thing here, which shows that we have h bar over I, and yes, that I is the imaginary number square root of negative 1, times the first derivative with respect to x. And that does seem odd, but that's the basic of quantum mechanics, in that the operator for momentum in the x direction is this derivative with respect to x. So let's look at a particular example. Let's consider a wave function where psi is equal to e to the ikx. And let's say that I want to know the momentum. What are the possible outcomes of momentum when I go in the laboratory? So what I'm going to do is I'm going to take my operator for momentum and operate on the wave function psi e to the ikx. So I have this. And when I take the derivative, this is my result. All right. So one thing we'll note is that the i's cancel out. So I end up with kh bar times e to the ikx. Now if I take a look at this, what I'm going to note is that e to the ikx here in my result is my original wave function. and kh bar is a constant. So what I have is a situation where after taking the after operating on my wave function with a momentum operator, I get a constant kh bar times e to the ikx, my original function. So I do have an eigenvalue equation, and my eigenvalue is kh bar, is the constant. Now what does that mean? That means when I measure momentum in the laboratory, the value I'm going to get is kh bar. So there we see how we take an operator, we can operate on the wave function. If we get an eigenvalue, a constant, times the original function, that tells me exactly what I'm going to measure in the laboratory. What I'm measuring in the laboratory is kh bar. Okay, so let's look at an example where our wave function is not an eigenfunction, and we don't get eigenvalues when we do an operator. So in this case, we're going to look at our function sine of pi x. Now if we do sine of pi x and we ask what momentum outcomes will I get if I go in the lab and measure momentum for this particle. So I operate on sine of pi x with my momentum operator. And when I get this, all right, I find out that I get this result, h bar over I times pi, which is a constant. Hey, that's great. But cosine of pi x is my result. Now, superficially, you may think, okay, my eigenvalue is h bar over I times pi, so that's what I'm measuring in the laboratory, although one clue that this is wrong might very well be that I've got an imaginary eigenvalue, and you can't measure an imaginary result in the lab. So there's a problem here. But the real problem becomes obvious if you remember the definition of an eigenfunction, we should get a constant times the original function, but our function is cosine and our original function is sine, so we don't have a constant times the original function. So I don't have an eigenfunction. And when that happens, that means there's more than one possible outcome to my laboratory measurements. I'm going to get more than one possible result when I measure the momentum in the lab. All right? So how do I deal with that? Well, think about this. When you're in the lab and you get multiple measurements, what do? You average things. And so, yeah, we're going to average it. So how do I do that mathematically? Well, that's something called an expectation value. And the expectation value is very simply defined according to this relationship here, where O in the brackets represents an average, the little o. And then we've got an integral here, in the numerator and the denominator. The integral in the numerator shows us that we've got an operator operating on our wave function psi multiplied by psi star. All right. In the denominator, we've got an integral which is just psi star psi without the operator. Now we see this d tau. When we see that, that means we're talking about all space, whatever all space might be in a particular system. In some systems it might run from negative infinity to infinity. In other systems it might be different. And certainly we're going to see some differences when we look at specific systems. So let's take the example in this situation where we want to know momentum. And when we want to know momentum, what we're going to do is we're actually going to set up our integrals here for expectation values for the average momentum. And then we see we've got this situation, and we're going to apply it to the sine of pi x function that we looked at on the previous slide. And so we're going to have all space. Now all space, for reasons that we'll discuss later on in this particular example, is just 0 to 1. So it makes life a little bit easier. So we're going to integrate from 0 to 1, and we just need to substitute our function and operator into this equation. So our function was sine of pi x. The operator, of course, operating on the function sine of pi x. We did that in the previous slide, so we know the result of the momentum operator operating on sine of pi x is equal to h bar over I times pi cosine of pi x. So we've already done that, so that we just put into that equation. The denominator, of course, is just a sine of pi x squared because our wave function is real. Right, so we can go ahead and plug this into Wolfram Alpha if we choose, and we find that our numerator has a value of 0 and our denominator has a value of 1/2. So overall, the average expectation value is equal to 0. All right, well, what does that mean? I have more than one possible outcome in the lab, but the average is 0. Well, remember, momentum is a vector quantity. It can take on values which are plus or minus depending on the direction of the particle. So in this situation, we simply have a system where the particle is allowed to go both directions, and the momenta just simply cancel out so that the average becomes 0. So this ends our video with a simple discussion of operator algebra and the Schrodinger equation. We'll be looking at these things in more detail and looking at more concrete examples in future videos.